G Lounge is here today visiting with Professor Dennis Choi, the Director General of the Brain Science Institute here at the Korea Institute of Science and Technology, better known as KIST, in Seoul. Professor Dennis Choi is an expert in brain science, one of the leading researchers, and we'll learn a little bit today about recent developments in brain science and the prospects for the future. Welcome, Professor Choi.
Thank you. Pleasure to be here.
So we'd like to ask you first a little bit of your insights about one of the topics of great interest these days, the breakout of the Zika virus and its potential impact. There's been a lot of concern about this. Tell us a little bit about what this virus is and what the potential is for treating it and preventing it in the future.
Well, sure. I'm a neurologist, not a virologist, so I can't pretend to be an expert on viral biology. But my understanding is that this virus has been implicated in causing microcephaly, a real tragedy in babies born to mothers who were infected with this virus during their early pregnancy.
With an exceptionally small
Yes, that microcephaly, small head.
Right.
So it's really a very sad thing. It's not 100% clear that the Zika virus is the only agent responsible for this outbreak of microcephaly, which has occurred primarily in Brazil. But it appears to be a major cause.
And your sense in terms of what the response might be or what the possible treatments?
Well, I think everybody's scrambling to try to manage this great threat. Right now, as far as I know, and again, I'm not a virologist, but my understanding is that the best advice is to avoid exposure by trying to stay out of the areas where the Zika virus is being actively transmitted by mosquitoes, and of course to take the usual anti-mosquito precautions, wear clothing and use spray. But there's no treatment for the Zika virus.
So recently you've been talking a bit about the issue of strokes and the response and long-term treatment for strokes. Can you tell us, this is of course another very different but very terrifying threat that we all face. What are the prospects for new treatments? What sort of new innovations are out there now?
Well, stroke's a little closer to what I deal with on a regular basis. Stroke is a terrible problem worldwide. It's the third leading cause of death in the West and probably the second leading cause in Asia.
Interesting.
The good news is that there has been recent progress towards managing stroke, first in prevention. So we know more and more about the risk factors for stroke, and managing these risk factors, things like high blood pressure or smoking or diabetes, diet, exercise, have been responsible for steadily reducing the prevalence of stroke in a number of areas, in particular in the northeast or western areas of the United States. There's also been recent developments towards acutely treating stroke, intervening, and the treatments that have been shown to be effective.
Immediate response or is it long-term?
No, this is very much immediate response, are so-called clot buster approaches. So these approaches are only usable in a subset of patients, but in people who get to the emergency room with a certain type of stroke and get there quickly enough, it's possible that a medication called TPA can be used to bust the clot open and restore blood flow to the brain. And just recently, a number of medical devices in the hands of surgeons have been shown to be also effective in this subgroup of patients.
Not for hemorrhages, but for blood
I should,
clots.
Maybe by way of general background, I should say what a stroke is. A stroke is caused by a disruption in the blood flow to the brain. In most cases, this is a blockage. Think about a pipe and a plug in the pipe. But in a minority of cases, maybe 15% of the time, it's caused by the pipe rupturing, and that's a hemorrhage.
In terms of long-term care?
Long-term care is, there's more slow progress in that area. There have been some recent studies suggesting that there are things that can be done following a stroke to aid recovery. But we're at the earlier stages of that kind of therapy.
Do you have any sort of general advice? I mean, I've heard winter is a time that there are more strokes and there are certain activities, there are certain population groups are at greater risk? Any advice you have in terms of preventative action?
Well, I mean, this goes back to doing the things that one can do to manage risk factors, which are actually very important. The single most important thing would be blood pressure.
Right.
So it's very, very important that people, and that's all of us, because we're all at risk for stroke, be seen regularly to ensure that if we have high blood pressure, which is a very common condition, especially actually in Asia, it's probably all the salt and the soy sauce.
Right.
It's very important that high blood pressure be managed. In addition, there are other medical conditions that can predispose to stroke, like diabetes or high cholesterol and things like that, smoking. Diet and exercise,
absolutely,
very important.
And then there are some other diseases which have been much more problematic, harder to deal with, long-term degenerative diseases like Alzheimer's and then Parkinson's.
Yes.
What is the state of the research in responding to these, both in terms of preventative and in terms of treatment?
Okay. There's been progress in the preventive area. So in a similar fashion, diet and exercise and actually using one's mind are all now thought to be useful in staving off the onslaught of something like Alzheimer's disease. But if I were to put these kinds of diseases together, these are all neurodegenerative diseases. Diseases in which the neurons in the brain die before their time. You don't want them dying before you do. If they start going before you do, then you can start to lose mental capabilities. That's one of the great frontiers in medicine, not just neurology, is basically crossing over into finding therapies that can slow these diseases down, protect the brain against the ravages of these diseases. But we don't have such treatments yet. They're in the pipeline. But we do know how to reduce the risks with preventive measures. Diet and exercise, again, prominent.
These are very basic.
They're basic.
Are there any specific, say, medications or treatments that also have a preventative effect?
Well, in a sense, yes. I mean, to the extent that, for example, cholesterol is probably a risk factor. Cholesterol-lowering agents, statins, are probably useful. It's not 100%.
For both Alzheimer's and for Parkinson's?
More for the Alzheimer's side. And certainly, there are risk factors associated with both Parkinson's disease and Alzheimer's disease. But I want to say that there actually are effective treatments for these diseases. They're just not they're not disease-modifying treatments. So there are medications now that are, I would call it, in the foothills of therapy. They've just been shown to produce benefits for certain patients with these diseases, and they ameliorate symptoms. But they don't change the overall progression of the disease. And so these medications are available newly for Alzheimer's disease, or within a few years ago. And Parkinson's disease, actually, of course, is far more advanced. It's fairly routine for physicians to be able to manage Parkinson's disease with drugs like L-DOPA, and more recently with deep brain stimulation, to ameliorate symptoms, actually for quite some time. Unfortunately, the disease itself is unaltered and continues to progress. And so that's what we're looking forward to in the future, is being able to change that actual progression.
What about possibilities, say use of stem cells or other possible?
Yeah, that's a great question. That's in a sense the next great frontier after slowing the disease, because stem cell or cellular replacement therapies, which are being studied now in animals and in some limited clinical studies, have not only the potential to disease modify, but potentially the ability to restore. So you could imagine that, at least in theory, it would be possible to bring back some of the circuits that have been lost to Alzheimer's disease or Parkinson's disease. That would be fantastic.
And are you thinking that's like 10 years or 50 years? How far out do you think that would be?
That's a little harder to pull out of the crystal ball. Parkinson's disease is probably easier than Alzheimer's disease, and there are some early studies suggesting some benefits with cellular therapy, really reconstructing lost circuits for somebody who's already gotten midway down a degenerative process. That, unfortunately, is probably not in view at the present time.
I guess in the case of Alzheimer's, you couldn't actually restore memories. You can only restore the ability to remember,
That's right.
So another disease which has been discussed considerably is on the other side, for young people, is autism, which affects something like 1% of children and can be extremely serious and tragic impact on people. Of course, there's a whole range,
spectrum,
a spectrum
right.
of states, right?
Absolutely.
So tell us a little bit about where we stand in terms of our understanding of autism, the diversity, sort of, I guess it's a whole sort of a family of different conditions, and what are some treatments that are viable now and what might be possible in the future.
Well, you've outlined it perfectly. So autism is of great concern now worldwide because it does appear that the prevalence is rising.
Right.
So it was a number of years ago thought to be quite rare.
Right.
That's certainly not the case today.
Right.
And the most recent estimates in various countries indicate prevalences of greater than 1%, as you
right.
said. In fact,
that's high.
That's very high.
Yeah.
In fact, the world's first population-based study, which is the most rigorous way to look at
right.
prevalence, you go knocking door to door, was carried out here in South Korea by Professor Kim at Yale.
Right.
And she came up with a number of over 2% in South Korea. When that was just a few years ago, when that more than 2% number was published,
right.
everybody thought it was either wrong or it might relate to an extra high prevalence in Korea.
Right.
But that may not be the case. The U.S. number is now catching up, and the most recent prevalence estimate from the CDC is now about 1.5%.
So when you say catching up, you mean in terms
climbing.
of it's increasing or the thoroughness of the investigation?
That's not 100% clear.
Right,
That's exactly right.
Right.
Most people, so we don't know for sure.
Right.
Most people, including myself, think the prevalence is increasing. These increases
right.
are just too great for it to be
right.
purely ascertainment.
Right.
But ascertainment certainly plays a role.
Understood. So one of the issues which has been much discussed is early efforts, early intervention in terms of autism. So
yes.
what are the ways of determining whether autism is present and how to treat it early on in the evolution of the development of a child?
Those are the key questions now.
Mm-hmm.
So the good news again here is that the field has really dug in hard on autism because it is now recognized to be such a major problem, so
right.
common, and
right.
so in some cases so devastating.
Right.
So there's been an enormous amount of neuroscience research
right.
on the causes of autism, and a great deal has been learned. In just
right.
the last few years, autism has moved from being a black box to something that really
right.
we know a lot of the components, a lot of the risk genes, things like that.
Right.
Therapies lagged, as one would expect, but we were starting to see the beginnings of effective therapy. At this point in time, the therapies which seem to work, again, just as you said, it's very heterogeneous, so not for everybody, but
right.
for certain selected right. individuals, the therapies that seem to work are behavioral interventions.
Right.
So that's just what you said. The earlier these interventions are put into play, potentially the more effective they can be. But
right.
what is really the bigger part of the therapy equation
right.
will be the biological therapies that are aimed at modifying the disease process. It's a neurodevelopmental disorder,
right. Right.
meaning the child or the baby's brain hasn't quite developed right.
Right.
And so it's a tough challenge.
Right.
Because you have to sort of undo some of the things that have happened over a period of time. It's not just a point of intervention
right.
affair. But there are strategies for doing this. Some of them look promising in experimental animals. Mm-hmm. And so I think we will progressively see therapies that are very much needed for this disorder.
Well, I myself used to volunteer working with autistic children, so I have a
Wonderful.
little experience, and I know that it's quite difficult because you don't get an immediate response. You have to continue to engage the child for hours and hours, and you may get eventually, but it's not as transparently clear that you're
exactly right. It's the core.
Right.
That's really the core of autism is a deficiency in social interactions.
Right. And often I found the kids they appreciate it in fact.
Sure they do.
But they don't express it. They don't
Right.
express it.
Often don't make eye contact. So
Yes.
so you have to understand that and work through it.
So are there any other neurological diseases that you've been working on or considering that we should be aware of?
Well, unfortunately, there are a lot of
them.
neurological diseases. Depends if you're a lumper or a splitter.
Mm-hmm.
But even if you're a splitter, there are thousands of diseases
Right.
and there are thousands of causes, et cetera. But even if you're a lumper and you just say, well, let's just put them together in broad categories,
Mm-hmm.
there probably are many hundreds of different brain diseases.
Right.
Brain diseases as a whole are enormously impactful, probably the single most impactful category of diseases on humankind.
Right.
The best estimate for the impact of brain diseases on people today comes from Europe, actually. They've done the most rigorous study. And a few years ago, their best number for impact today in the first world, Europe, was basically in sort of round numbers, something like a third of all individuals, actually it was a bit more than a third, were affected by diseases of the nervous system.
Interesting.
And the impact economically, which is another way of looking at impact, was sort of correspondingly about a third of all expenditures, both direct and indirect healthcare expenditures, were for diseases of the nervous system. So that's the sort of.
Do you extend, I mean, I guess there's a sort of a blurry line between the psychological and the neurological. Do you have a point at which when you say a third, does that include, say?
Yes, no, it very much does. There's no blurry line at the level of the biology.
Right.
The blurry line only comes essentially historically, when in an earlier era, and we didn't really understand the brain as well, we thought of neurological diseases and psychiatric diseases as different.
Right.
Today, really, of course, it's the same organ, and a problem in the brain can manifest itself as motor weakness, or it can manifest itself in anxiety. And really, it just depends on which circuit is hit. Is it the circuit that controls our movements, or is it the circuit that controls mood and equanimity?
Well, I mean, for example, attention deficits, various forms of psychosis, compulsive behavior, these are all
brain diseases.
All brain diseases, as you see them.
Right. So it truly is one and the same at the level of the biology. And yes, so all the numbers now that look at brain diseases are a combination of so-called neurological and psychiatric diseases. And to be fair, of course, the nervous system is a little bit bigger than the brain. So the nervous system would also include the spinal cord, and there are very important diseases of the spinal cord trauma, or amyotrophic lateral sclerosis. In the U.S., it's often called Lou Gehrig's disease, after the famous Yankee baseball player. But these are diseases of the spinal cord. In the case of Lou Gehrig's disease, it also does affect the brain, but oftentimes the biggest impact is in the spinal cord. You can get diseases of the nerves that come out of the central nervous system. Those are called neuropathies. And since it's all sort of one excitable tissue connection, we neurologists also treat disease of muscle. And so the purview of nervous system diseases is really brain, spinal cord, nerve, muscle.
Right. So that's a pretty good overview. The specific term brain science that you use, say, for your research center here, how do we define brain science as opposed to, say, neurology?
Well, neurology is a medical discipline. So neurology would be, by convention, would refer to a certain set of diseases. Brain diseases, I think, is the comfortable way of describing diseases that affect the central nervous system. A more technical term, which is largely synonymous, would be neuroscience.
Right. But I mean, specifically, when we look at, say, brain science, there are efforts on the other side. That's to say, with rapid technological change, there have been new evolutions in terms of computer science, what's called the fourth industrial revolution, or industry 4.0, with all this potential for artificial intelligence, sort of reverse engineering the brain as a way of creating new services, systems, products.
Yes, so that would be an extension of neuroscience out of the medical arena. The purpose of neuroscience, of course, is not entirely just to treat diseases. You could say that really the core purpose of neuroscience is for man to understand man. It's really to understand ourselves. We are our brains. And so that really is the broad frontier. Treating diseases of the nervous system is an important goal, but it's not the entirety of neuroscience. And there are very important interfaces of neuroscience with other disciplines, and you just cited one of my favorites, which is the connection between neuroscience and computers or robotics or artificial intelligence. And I think that's really, what you said is really as I understand it, I'm a neuroscientist, not a computer scientist, but my understanding is that the computer scientists are really getting more and more excited these days about taking the approach which you outlined. In other words, in an earlier era, computer scientists as I understand,
Right.
believe that they could pretty much accomplish any goal in artificial intelligence by making just bigger, faster computers.
Right,
And they've begun to realize that that's probably not going to work. And so there's more and more interest in computer science now in basically reverse engineering the brain.
Right.
Somehow or other we do all the wonderful things that humans can do with about 3 pounds of wet tissue in our
Right.
skulls.
It's pretty
and
amazing.
yeah, and it doesn't require a whole lot in the way of energetic support.
That's
you
true.
know, a little rice and kimchi from time to time. And so, you know, the computer scientists are looking at that saying, okay, there've got to be some principles there that we can understand and basically leverage into artificial devices that would be more capable than our current computers.
In terms of the next generation of, say, devices or approaches for treating brain diseases, do you think some of that artificial intelligence know-how can serve a complementary? I mean, I know certainly there are people who are able, like paraplegics, who are
Yes,
able to walk
absolutely.
with exterior skeletons. What are some of the possibilities?
Yeah, absolutely. So this, I guess, one general term for this interface field, this is back to the medical side,
Yes.
would be brain-computer interface work.
Brain-computer interface.
Right. And so the kinds of things that are being done today are, as you described, there are people looking at trying to tap directly into the brain
Right.
and use it to control effectors, such as, you know, artificial limbs and the like.
Right.
I saw a video recently, it was marvelous, of a woman who was locked in,
Right.
which means she was conscious but had no ability to move her own arms and legs. So sort of think of it as a very high spinal cord injury.
Right, right.
And they were able, the investigators in this study were able to tap into her brain, and then she was able to control an arm, and she was able to take a
Interesting.
sip from a glass of water. And of course you have the cochlear implant, could
Right.
be thought of as an early one
hearing.
of these for hearing, and we are probably at the foothills of artificial sight.
Sight
And
as
that,
well.
that would be a camera type device that would essentially interface into the nervous system so
Right.
that a person who's blind
Right.
and in particular on the basis of a retinal problem
Right.
might be able to have some functional vision again.
Right. And you see that as not being too far in the future?
No, this is being done now.
Right now.
Right.
Very
So the
exciting.
prototypes are being developed, and in fact, there's a device being marketed now.
So to support these sort of efforts, of course, requires a long-term vision and
Right.
long-term commitment to funding. What are your thoughts in terms of how countries, how institutions should go about this long-term investment? And then specifically in the Korean case, what do you think Korea needs to do to make sure we have a long-term vision and long-term support?
Well, I'll start with your latter question. I mean, I would certainly love to see Korea continue to invest in brain science. It has made remarkable investments over the past 5 to 10 years.
Right.
And the Korean neuroscience community has really prospered and grown as a result.
Right.
So I would, as a neuroscientist, which is not entirely unbiased, I'd love to see this continue. And I'd like to, and I think neuroscience is a field of sufficient breadth and complexity that that progress in neuroscience would be best facilitated
Right.
with systematic level investments. You know,
Right.
as you know, in the United States, this has occurred fairly recently. President Obama, in his 2013 State of the Union address, launched
Right.
the U.S. focus,
mapping.
brain mapping initiative. It's now called the BRAIN Initiative. That's the acronym.
Right.
But it's a very ambitious
Right.
project, and it's got the current strategic planning horizon is about 10, 12 years.
Right.
And the price tag on that, I mean, basically no one knows, but
Right.
the sort of ballpark at this point in time, even just on the NIH side, which should only be part of the overall U.S. investment,
Right.
they're scoping it out at something on the order of $4.5 billion over about the decade.
4.5 billion.
Billion, yeah.
So that's not I mean, it's a lot of money for us, but it's
That's
not
right.
an enormous amount of money. In terms
Absolutely.
of- yeah.
It's not a lot of money in the context of big national initiatives.
Right, right.
So the U.S. comparator would, of course, be the moonshot,
Right,
the
yeah.
Apollo project.
Right.
And in today's dollars, I think the Apollo project's cumulative tab would be close to 100 billion.
Right.
So
right.
yeah, 4.5. But of course, that's not the entirety of the investment. but
And how do we
it's-
convince taxpayers, ordinary citizens, to see that this, without immediate returns, but this is really a long-term essential project to fund, to support?
I mean, this is basically the kind of goal that I think everybody can get behind when they understand it. So I see the task ahead as one of communication and ensuring that the public, really the global public, are included in the effort and can get excited by it. The public supports research efforts designed to better understand who we are and where we are. We've just heard about the great success with detecting gravitational waves.
Right, I saw yesterday.
Yeah, that was a $1.1 billion NSF investment over many, many years.
Right.
There's probably no immediate benefit to you or me or anybody that we know from knowing a little bit more about gravitational waves.
Well, it took 100 years.
But neuroscience, in fact, does, of course, have some fairly immediate implications for health benefits. So I think the public in America or in Korea could easily get behind a big initiative in this area, or, if appropriately informed and included in the planning process.
So we're, of course, today talking with the general citizens of the world about the issue of brain science, specifically brain mapping, which is a term which may not be so familiar for everybody. Can you say a little bit about what this field is and why it's so critical?
Sure. Brain mapping basically recognizes that we now have enough understanding of how the brain works and enough technical capabilities that it's possible to envision a strategic project that would identify the connections of the brain at a single cell by cell or connection by connection basis. So it's a mapping experiment.
It's equivalent to the Genome Project in that respect?
Conceptually, I mean, it's very different, but both projects are big science projects that required a lot of coordination, couldn't possibly be done by any single institution. So it required sort of federal level efforts. Really, in the case of the Genome Project or the Brain Mapping Project, global efforts. So the U.S. Brain Initiative has a counterpart in Europe, and that's the Human Brain Project. And Korea is beginning to make significant investments in this area as well. Here at the KIST BSI, there's a Center for Functional Connectomics, which examines some facets of the mapping challenge, which are very well positioned to help the global effort.
Now, the famous physicist Stephen Hawking recently raised concern that the development of artificial intelligence could be the end of humanity. And there are those who have voiced a sort of a more pessimistic view of the prospects of the future. What are your views on this issue?
Well, of course, all knowledge and certainly all technologies can be used for evil as well as good. So it is an incumbent responsibility to use technologies properly. But I think, with all due respect to Professor Hawkins, that's a bit of a dramatic statement. I think we're a ways away from such a point. That's Skynet, Terminator movies.
Well, so movies are a place we see these sorts of imagined potentials. For example, the recent movie Inception talks about how ideas can be implanted in people's minds. And there's also a movie, Lucy, which came out, I guess, about a couple of years ago, about how sort of memory capacity could be enhanced, perhaps artificially. What is your sense in terms of the potential of these as actually being real technologies, real approaches in the future?
Well, I think that there are visible strategies now for enhancing memory a bit or influencing inclinations. But these are miles away from the kinds of control scenarios that have been popularized in movies. But still, I would go back to the general responsibility that scientists always have, which is to do their very best to ensure that new knowledge and technologies are used for good and not for evil.
And specifically, or more generally in terms of brain science, what do you think the greatest contribution potentially is for the future of humanity, for the future of humans?
Well, the great possible potential of neuroscience for humankind is really self-understanding. If you think about all the work that's being done in the area of physics and space exploration, which I am fascinated by and deeply support, that's the external frontier. Essentially, we want to know, where are we? But before you can even interpret the answer to that question, you have to ask an earlier question, which is, who am I? And we are our brains, and everything we experience is in the context of our brain's capabilities. So really to understand ourselves, and then you could start getting practical and say, you know, to understand our limitations and perhaps ameliorate some of the diseases, we need to understand brain biology, neuroscience.
So let's take a look at the actual concrete activities of the KIST Brain Science Institute. We have a short video here that gives us some of the details.
The Brain Science Institute of the Korea Institute of Science and Technology has produced a noteworthy outcome from one of its research and development projects. A research team led by Dr. Bradley Baker has developed a protein sensor that can detect changes in membrane potential for real-time observation of brain activity.
We want to measure voltage optically, so I'm attaching an electrode to the cell so that we control when the voltage will change.
The protein sensor is a fusion of voltage-sensing proteins and fluorescent proteins. The voltage-sensing domain in particular has been modified to measure and record brain activity at 5 times the speed of conventional neuronal sensors.
And then we look at the fluorescence change in the cell. And now you can see that the fluorescence got a little bit dimmer and then really dimmer, and then it activated and got brighter. Got dimmer, brighter, dimmer and brighter, dimmer and brighter. So we call this probe POTO because the fluorescent signal looks like a wave.
Dr. Baker explains the components of this technology using Korean words such as tonagi, pado, and 봉우리 that mean sudden shower, wave, and peak respectively.
Well, if you use your imagination a little bit, a fast spiking pattern, when you image it and it has fluorescence, you'll see it looks sort of like a mountaintop. And since that's how we came up with 봉우리.
Dr. Baker explains changes in thousands of neural circuits can be observed in real time using 봉우리. This allows mapping of brain activity, being a facilitator in identifying the causes of brain disease and developing treatments for them. There is another achievement of KIST Brain Science Institute that has come under the spotlight. Dr. Kim Young-soo's research team successfully developed a technique to extract and analyze beta-amyloid peptides found in the brains of Alzheimer's patients as a way to diagnose Alzheimer's disease through a simple blood test.
My colleague, Dr. Hwang, who is also at KIST, developed this system that can detect beta amyloid in the blood in sub-picogram per mil. We finally made a blood test kit slash system detecting Alzheimer patients in about 95% against normal controls.
Last year, Dr. Kim's research team developed the world's first orally administered Alzheimer's drug with zero toxicity that eliminates the underlying cause of the disease, which is beta-amyloid proteins.
It has a power to open up the market because there is no market for all Alzheimer drugs. So if we succeed in the clinical trials, which is really, really low chance, but if we succeed, we have a very high chance to conquer the market of Alzheimer drugs.
The Korea Institute of Science and Technology, which became the first to initiate brain science research in Korea 15 years ago, is fast becoming the nation's brain science research hub, with more than 280 researchers dedicating themselves to related research and new drug development.
So what are some outstanding activities, achievements here in brain science research in Korea?
Well, I don't have a perspective on all of Korea, but I've had the privilege of working at the KIST Brain Science Institute, BSI. And the BSI is engaged both in basic blue sky neuroscience as well as translational neuroscience.
Right. Maybe you can say a word about what those terms mean.
Sure. Blue sky neuroscience is neuroscience directed at understanding the brain,
Right.
devoid of any immediate targeting of a purpose, really
Right.
just what is our brain about?
Right.
And then translational neuroscience means how do we take some of the discoveries from basic neuroscience and make use of them to help people do the things that they do, in particular and most importantly, manage diseases of the brain.
Now, let's take a step back and talk a little bit about your own experiences. So you originally were a major in electrical engineering at Harvard, and then you went on actually to get an MD and follow a different road as a physician in medical school. What attracted you to the neurosciences? What was behind the path that you've taken so far?
Well, I guess I did go to college thinking I would be an engineer. My dad's an engineer, and I thought I would be an electrical engineer.
Right.
And then I got interested in biology, and those two essentially translated next into an interest in neuroscience.
Interesting.
The brain is really the electricity side of,
Right.
of biology.
Right.
So I gravitated towards neuroscience, I think reflecting my fondness for electricity.
Right.
And then as a budding neuroscientist, the engineering pull started pulling me towards medicine, and that's how I ended up becoming a physician.
So you mentioned your father, Professor Choi Yonghua. Tell us, who had a role here, of course, at KIST in the founding. Tell a little bit about his experience and how he may have impacted your own career choices.
Well, my dad is a mechanical engineer, and so really that admiring him and watching his career had me thinking when I was growing up that I also wanted to be an engineer.
Right. So looking forward in terms of the KIST Brain Science Institute, what are the short-term and 2016 and long-term goals and vision?
Well, the KIST BSI seeks to continue to contribute in both of these arenas, basic neuroscience, probably most focusing around the global brain mapping initiative,
Right.
as well as some frontier work that is going on today in the BSI, looking at glial neuronal interactions. And then the BSI also will likely maintain its other focus in translational neuroscience. And a strong example of that today are the current programs in the area of Alzheimer's disease, where the
Right.
BSI has some exciting leads towards identifying so-called biomarkers for Alzheimer's disease. That would be potentially a blood test that would help
Right.
determine whether somebody does or does not have Alzheimer's disease,
Right.
as well as potentially a therapy for Alzheimer's disease. Of course, we would all like that.
So going forward, in terms of development of the brain science, what are some decisive factors? For example, global collaboration, I think you're suggesting, is a
Yes.
major one. What should we look for as the deciding factors?
You've already picked number one on my list.
Yes.
Neuroscience has gotten to be big science, and both technically demanding and
Right.
conceptually demanding at an informatics level. So I think we're well past the time when it would be likely that one could make a contribution alone in one's basement.
Right, right.
So for KIST to continue to contribute on the global at the global level, it will need to maintain and strengthen its partnerships with other institutions and other groups of neuroscientists around the world. And this is happening. This is very much part of the BSI's plan.
Now, I'm sure there are some of our viewers today, young people who are interested in the sciences and particularly in brain science. Do you have any particular advice you'd like to give those individuals who are taking a real interest?
Well, I don't ever feel that I'm in a position to offer anything other than my own experience. My own experience, I would say that I've always felt that I did well by following the things that fascinated me. And
Right.
so it's really a follow one's nose approach to life that has given me wonderful opportunities, and I would recommend that approach for others. I think that one should be overly prescriptive about what one goes into. As long as one's enjoying what one
Right.
does
Right.
and feels that one is making a contribution,
Right.
that's good.
Well, that has been a very fascinating discussion of a very, very important topic, brain science, and I think we've learned quite a lot about what KIST, specifically at the Brain Science Institute, is doing today, and also what the implications are for humanity as a whole of this incredibly important work. Thank you for joining us, Dr. Choi.
Thanks for having me.